In this video, I'm going to talk about the regression model assumptions, and these assumptions relate to the random errors in the model. So remember, the random errors in the model are equal to the difference between y and expected y. So in other words, y minus b0 minus b1 x. And these represent the part of the model that isn't deterministic. So it's picking up all the variation in y that's not accounted for by the predictor x. So there are four assumptions, and these relate to the probability distribution of the errors at each value of x. The first of which is that the probability distribution has a mean of 0. Sometimes this is described as a linearity assumption. Next one is that the probability distribution of the random errors at each value of x has constant variance. The third one is that that probability distribution is normal. And then the fourth assumption is independence. So the value of a random error for one observation is independent of the value of a random error for any other observation. So one way to think about these assumptions is on the scatter plot of the data. So I mentioned before that we can pretty much see everything that's going on in the scatter plot. So if we think about the scatter plot here with y on the vertical axis, x on the horizontal axis is normal. The points are these points here marked, filled in circles. And then we've got the regression line. And remember, the regression line represents the expected value of y given x, which is equal to b0 plus b1x. And then what I've done here is I've drawn a line with a bell curve above it representing the probability distribution of the error term for each observation, so at each value of x. So there's one for each of the 5 observations in this graph, and this first one, so the point on the regression line, that corresponds to the most likely value of the error, the part at which the bell curve is at its peak. So, and remember, this normal distribution, it's centered at 0. That was one of the assumptions. And it's normal, so it's got a bell curve. And so if we look at each one of these, they're all centered on or above the point on the graph, point on the regression line, sorry. So that's the most likely value for the error, is right in the middle of the distribution, which is where the error is 0. So if the error was 0, the point, the observed y value, would be right on the regression line. It's usually not, it's usually off by a little bit, and it's off by the amount of the error. So this one's below the regression line, this one's a little bit above, this one's even more above, and so on. But on average, we expect all the errors to be 0 and for all the points to lie along the regression line on average. And the other thing to note here is that each of these normal distributions, these bell curves, they all have the same spread. So that's the constant variance assumption. So this picture here summarizes those first 3 assumptions, that the probability distribution of the error term at each value of x is normal with 0 mean. That means they're centered along the regression line, and with constant variance. And then that fourth assumption there, independence, we can't really show that in a picture. Okay, so those are the theoretical assumptions underlying the model. And so the idea here is that we would like to be able to assess the validity of those assumptions for any particular model fit to some data. So the way we do that is to calculate the estimated errors, which are also known as residuals. So these are given by this notation here. E hat is the residual, and it's equal to the observed value of y minus the fitted value of y. And the fitted value of y is given by the regression equation, b0 hat plus b1 hat x. So we calculate those residuals, so there'll be a residual for every observation, and then we can draw a residual plot that has those residuals along the vertical axis, and then the predictor values along the horizontal axis. And then we can assess the zero mean assumption by asking ourselves, do the residuals average out to zero as we move across the plot from left to right? Constant variance assumption, as we move across the plot from left to right, we want the variation of the residuals to be similar. And then we can also assess the independence assumption just by asking ourselves, do the residuals look random with no systematic patterns? The normality assumption, it's a little difficult to check in this residual scatter plot, so instead we can assess normality as a whole by either looking at a histogram or a QQ plot of the residuals. So we talked about those in chapter 1, and ideally the histogram should look approximately bell-shaped and symmetric, and on the QQ plot the points should lie along the diagonal line. So let me illustrate how to do that with an example from the end of the chapter. So these are body measurements. So we've got arm lengths and overall heights, and we're trying to establish a linear relationship between these two. So here's a plot of the data. So we're trying to predict standing height in centimeters from upper arm length in centimeters. Now we've got a whole bunch of data here, and it looks as if people with longer arms tend to be taller, people with shorter arms tend to be shorter. And it seems like there's a linear relationship there. So let's fit a model, summarize it. So here's the estimated intercept, here's the estimated slope. And then if I was wanting to use this model, before I use it, I do need to assess the assumptions. And we're going to assess the assumptions using this method here. So I'll draw that residual scatter plot. And I want to look at it a little more closely, so I'm going to save it as an image and then open it up so that we can look at it more closely. Okay, let's make it a little bigger. Okay, so and let me annotate this as well. Okay, so what I'm going to do is I'm going to divide the plot up into vertical strips or vertical bands. Okay, so I'm just doing this for illustrative purposes. It would be very tedious to actually do this every time you analyzed a simple linear regression model. But once I've illustrated what I'm doing here, you can actually apply the same kind of process without literally creating strips. You can kind of do it by eye. So what I'm doing there by creating the strips is it makes it easier to assess this zero mean and constant variance assumption. So the zero mean assumption asks, do the residuals average out to zero as we move across the plot from left to right? Okay, so first of all, take this strip on the left and think to yourself, okay, what is the average residual in that strip? So I've got one residual up here, a couple here, and one down here. So if I was to calculate the average residual for that strip, it would be somewhere here where I've got my pointer. Okay, somewhere close to 0. And that's what we would like. We would like the residuals to average to 0. Let's move to the next strip. So I'm moving across the plot from left to right. I'm moving into the next strip, and I'm asking myself the same question. The average residual in that strip, let's see, it's maybe a hair above 0. Well, actually I'm not sure, because there's this point down here. It's pretty close to 0, I would think. Next strip, let's keep moving left to right. Think about all the residuals here. Where's the average? Yeah, it's probably still close to 0. And in the next strip, I think it's still close to 0. And this penultimate strip, it's probably still close to 0. This last strip's a little bit interesting because I've just got 3 residuals here. They all look to be a little bit negative, so the average is going to be down here somewhere. The average for that last strip is maybe not that close to 0. It's not that far away either. But also, there's very little data up in this far right strip. There's only 3 points. And so I'm not going to get too concerned about anything I see in that last strip, because there's not very compelling evidence when I've only got 3 points there. For all the other strips, do the residuals average out to 0 as you move across the plot from left to right? Yes, I think they do. Okay, for the constant variance assumption, it's similar, except we're not looking at the average residual now, we're looking at the spread or the variance of the residuals. So kind of roughly, what is the range, what is the standard deviation, how far do they spread out? And does that stay constant as we move across the plot from left to right? So in this strip, we've got variability in the residuals from down here up to up here. In this one, it's a little bit narrower, but not much. This one, it's quite wide. This one, kind of in between. This one, maybe a hair narrower. And again, this last one, I'm not really going to pay too much attention to it. The variation is very narrow in this one, but there's only 3 points there, so I'm not really going to worry about that too much. Overall, is the vertical variation of the residual similar as we move across the plot from left to right? Yes, I think we can say it is. When you're assessing these two assumptions, you don't want to be too picky, because no plot is going to be perfect. You just want it to be good enough that you can say, I'm okay accepting this assumption. I could believe that in the population the zero mean assumption holds. I could believe that in the population the constant variance assumption holds. Independence, I'm just having a quick look at the plot, and does anything jump out at me as being very unusual, very systematic, very non-random? And nothing really jumps out at me here, so this is okay. Normality, so let's go back to R and let's draw a QQ plot. Well, let's draw a histogram first. Is that roughly bell-shaped and symmetric? Yeah, maybe. A QQ plot's a little bit easier to use. Do the points lie roughly along the diagonal line? I should say so, yeah. Okay, so that's an illustration of how this works in practice. Here's some examples of residual plots which are perfectly fine. These all pass with flying colors. If you stared at any one of these too long, you might be able to see some non-random patterns, but there's nothing to worry about here. Whereas these plots are ones which fail. If I was to divide this plot up into strips and think about where the mean residual is, the average residual in each strip, it starts off high, comes down, gets lower, gets quite low in the middle, and then rises again till it's quite high again on the right. So this would fail the zero mean assumption. This would fail the zero mean assumption in a similar way, only we've got low on the left, high in the middle, and low on the right. This one starts low, goes high, gets low again, goes high again. So this one's quite a complicated pattern that violates the zero mean assumption. This next row, these violate the constant variance assumption. The variability on the left in this graph is very small, and it gets bigger on the right. This one's the opposite. The variation starts quite big on the left and gets much smaller on the right. This one, the variability is large on the ends and small in the middle. So all three of these violate the constant variance assumption. These ones in this row, these actually violate the normality assumption. It's a little bit hard to see in this scatter plot, so we'll see plots of these data sets in the next couple of slides when we look at histograms and QQ plots. And then these last ones, these violate the independence assumption. I've joined the residuals up here just to get a better sense of why they violate the independence assumption. In this graph on the left, the residuals are tracking each other too closely. They're not jumping around randomly enough. Whereas this one, they're jumping around too much. It starts positive, negative, positive, negative. They're just jumping around way too much. And then in this one, there's something funky going on here because we've got a smiley face. So we shouldn't expect to see any systematic patterns in residual plots. Here's some histograms. The upper three are good enough to pass. The lower three actually fail. This one's interesting on the bottom left. You might think, well, that's a bell shape and it's symmetric. Turns out that there's too many values close to zero. No, actually this is the opposite. There's not enough values in the middle and we've got really big tails. So this isn't quite the right kind of bell shape. Okay, you're never going to detect that in a million years in a histogram, so we'll see in the next slide that it's much easier to detect this kind of problem with a QQ plot. These ones are a bit more obvious. They're obviously highly skewed. Same data, but looking at QQ plots, the top three are fine. These two over here, these are the skewed distributions. They're not fine. This one is this histogram. This is what the QQ plot looks like. So it's much easier to see why this one fails. We've got these points in the tails that are too far away from where they're supposed to be. So assessing assumptions in practice is actually very tedious and time-consuming and difficult because it involves opinion. It's not at all objective, it's quite subjective, but it is worthwhile doing, and the more experience you have doing this, the easier it'll become, the quicker it'll become, and the easier it is to make decisions. Okay, this plot is fine, but this one isn't. The rule of thumb that you want to do, what you want to use here, is you only really want to get excited and want to reject a model because it's violating one of the assumptions if there's a very clear indication that one or more of the assumptions is violated. Okay, don't get too hung up on tiny little things that you might see because more than likely everything is fine and you're just seeing a little bit of a glitch. You really only want to question the assumptions if something is really extreme, and examples of things that are really extreme are given here and in these QQ plots down here. We'll talk about what you can do if you find clear violation of one of the assumptions later on in the course. And one thing to keep in mind is that regression results are actually quite robust to mild violations of the assumptions. Things only tend to go really wonky if you've got a very serious violation. Mild violations tend to be fine though. The other thing to note here is that this method about how to check the assumptions. It's only really workable in practice as long as n isn't very, very small or very, very large. If n is very, very small, you don't have a lot of data to work with and it's hard to see patterns. If n is very, very large, then there can be problems because you've got too much to look at. And so that can be challenging in those situations. So that's a brief introduction to the assumptions underlying simple linear regression and how to check those assumptions in practice. And we'll revisit this when we talk about multiple linear regression in the next chapter. In the next video, we're going to talk about how to interpret your simple linear regression model results.